Hello everyone. Today I'm gonna model TMD in sap2000. I have seen many people asking this question, how to model TMD in sap2000, but there was not a clear answer. So I figured out how to model this. Before we go to the sap2000, let me give you some idea about the practical and theoretical concepts of this system. TMD is a very popular device which is attached in the top of the structure to control the wind and earthquake vibration. And this is type P101 with a very large mass in the top of the structure. The mass is hanging by cables, and in the lower part there is different type of hydraulic and viscoelastic damper. Here is the picture of the TMD, which is installed in type P10. This type of damper is viscous damper, and they are hydraulic dampers. And also in the bottom of this system is a source of isolation system, which can take the damper and these two damper can control the vibration of this mass. Which I said here is the block mass. The block mass, and this is the hydraulic dampers, and these two horizontal damper is also viscous damper. This is the original picture of installation and location of TMD, which is hung on by cables, and in the bottom is used some sort of dampers to attach with surrounded structures, and then it can control the structure movement. This was the practical, and I'm going to show you the theoretical concept of this. It is a book. You can find it written by Professor Connor, Structural Motion Engineering. Here is a very comprehensive detail of modeling, designing, and determining each of parameter. Just see, we have a single degree of freedom structure. This is our structure, and this structure is in a mathematical modeling represented by stiffness and damping, and another mass is attached above of this structure to control the vibration of this structure. So we should define this mass, how much mass we should attach to the structure which can suppress the structure vibration, and also what type of device should use to suppress these mass movements, which is in type E I have shown that can be hydraulic damper, that can be viscous damper. Each of these viscous damper and elastic hydraulic damper has stiffness and also damping. This is a long term of equations. You have to determine the frequency and the period of this structure. Then you will find the frequency and period of these masses. Then from this mass you can determine the stiffness is required. The stiffness is required to control this mass, and also the damping coefficient. If you couldn't find this book, I will please put a comment in the in the description in the comment area. Then I will upload this book for you. So this is the theory of mass damper. So we will go to the modeling of this damper. Let's unlock this model. I already built this model. This is a simple 2D frame. I use the default cross section. The thing is which I found I should determine is the total structure weight. The total structure weight is the vertical reaction of a joint. So if you get this reaction, then you can determine about 1% to 10% mass to apply as a TMD structure. When you have 100 when you have the mass of the tune damper, which I applied in this region, I draw a joint here. I draw a joint, and then with a length, with a length properties. So the length properties is represent the two cable and dampers. So the lower part is damper and the upper part is cable. So this is restrained above of the structure, or maybe another region which can control the movement of the cable. Just we allow to this mass should move, and this device should have stiffness and damping to control the movement of this mass. So here we define the link properties. The link properties, actually I defined two. I'm gonna delete this one. Is I define based on the total structure weight. Now it is depending your project. Maybe you can use 3D model, and also you can use this for a very big project. So then your total mass will be different. After that, you can define your mass and then determine this parameter. So I choose linear elastic link, which is allowed to define in three direction properties. The first part is I used is uncoupled with different mass. You can based on the mass of tune mass, you can determine this K1, K2, K3 in different direction. But the most is this K1 should be determined, and also the damping of this mass, the coefficient of this mass. So I already defined this mass, which can tune the structure and suppress the structure vibration. This is the properties I defined to the mass. But you can use different link to attach the upper part of the tune mass number. But for simplicity, I used one link for both. Now it's okay. Now we can see the link here. Is it a link 1 or no? Yeah, this is line 1 or link 1. We are completed with modeling of ordinary structure and with structure with TMD. So now we go to the define some function, time history function, to see the response of the both structure. So I already defined. One is cosine function, with a time period of 1 second, and a total time is 5 seconds. So this property is you can apply as much as you want, but you should be careful with structure height, because structure with height has proportional impact with period and frequency. So, and the second is a recorded function. I choose from file, and also you can bring this file from your computer. This is your move function. Here you can apply it. Time history function is here. Move. It's about 4,000. It's a very a huge earthquake, ground motion. It's recorded. Then you can go to the define some load cases. Here is your allowed to do linear analysis, also nonlinear analysis, but nonlinear analysis much more reliable and interesting. So I defined a function here, time history with nonlinear FNA. I defined the U1, the function you remove, and it's about 4,000 point, and is about 0.2 second steps. So I consider 5% damping of the for the structure, for the original structure, and then we will see the response with the tune mass damper, how much it increase the structure response. And the second is time history for cosine. Is about 5 seconds. I used 100 point, is about 0.5 seconds with scale factor 1, nonlinear choice. Okay, now everything is done. Just go to run. Also, you have to define the model, but I already defined this easy part of the model analysis. Yes, this is the structure response. The first deformation is the cosine. You can see in a first step, you can see the difference in U1 direction is about 5, join 9, and also the structure is about very small. To compare, it's meter. Let me choose mm. Yeah, and let me choose mm. This is about it's about less than 1 mm, and this is about also half. And before we go to plot something, you can note this is joint 9 and this is joint 18. So we go to the display, plot some function. So I already plotted. This is joint 9, which is the without tune mass damper structure, and this is 18 with tune mass damper. So now let's go to plot. Yeah, here is it. So how much it is impact the structure. So the joint 18 is the tune mass damper, seems very lower acceleration, and the red line which represent that without TMD, so it's higher acceleration. We can save this for our video recording. You can here is a you can change. Okay, and now we go to define some another function such as displacement. We can put 9. It can be displacement in u direction. Okay, and then go again, go to 18, and okay. So this is 92982 is the displacement. So we go to remove. Yes, shift is 2 together, and then see. Yeah, the same. The displacement is changed which is the maximum, is 240 millimeters, but in TMD structure is about half. So it seems about 50% decrease the structure response. This structure displacement. We also can save this. We can count this displacement. Okay, and let's see the cosine function, which is the same displacement. Yeah, here is it. The same changes made for cosine, since the TMD displacement is less, is about maybe 30% less than. And also we can see the acceleration. This too is acceleration. Yes, quite interesting. It's about 50 or 60% reduced the structure vibration. So there is some discussion on this part, this part, but I'm not going to there because the lower height structure, lower rising structure, the lower structure has some sensitivity for the short period. Now, for better understanding or visualization, we can make some video to see. But before this, I'm gonna display the so this is the display. Yeah, you see. Create video, and we can choose which, but I'm going to the recorded time is about 80 seconds, and the same 4000 point, and magnifier was 10. So it's sorry, but I'm going to stop it because I'm going to use one more things. This is the shoe graph. You can use the displacement, yes, and yeah, here is it. Sorry, it was displacement for. I'm gonna one more times displacement. Choose graph time history. This is it. Yes, this is a video, but I'm going to display shoe plot function. I'm going to here plot. Yes, I'm going to save this plot as time history year more. This is a year more, and add new plot. Okay. Okay, we go to again, create a video, and this time we choose time history year more. Okay, that's it. Yes. You can see the structure without a TMD is deflection more, and for TMD, just TMD is working we have to control the TMD deflection because it's very important. So for this recording, it seems deflection is very high. Yeah, it's done almost. I'm going to stop it. So this was the TMD modeling in SAP2000. You can apply this for a 3D project, but a 3D project will consume a lot of time to discuss. If there is any question regarding modeling of this and calculation, anything, and also if you're interested to have this model, I will please put a comment and I will give you this model. You can check in your computer. And thank you for your watching. If there is any question, please let me know. Thank you.